Hello viewers, my name is Dr. Ajay, Associate Professor from the Department of ECE, Institute of Aeronautical Engineering College, Hyderabad. Today we are going to discuss about the maximum usable frequency, the derivation of maximum usable frequency for curved earth, the basic definitions of skip distance, virtual height, and multi-hub propagation. We shall see these parameters of ionospheric propagation. So today's topic is maximum usable frequency, skip distance, virtual height, multi-hub propagation. So let us start our session today. Let us derive, in the previous session we have seen what MUF means. So maximum usable frequency. The maximum frequency at which a wave is returned to the earth for a given distance of propagation. So here, the distance is 10 kilometers, let us assume. The transmitter and receiver are fixed here for a distance of 10 kilometers. The maximum frequency at which a wave is returned to the receiving antenna for a fixed distance of propagation, we call it as maximum usable frequency. Maximum usable frequency. So here you can see here, if you take a transmitting antenna and if you take a receiving antenna, the distance is taken as 10 kilometers here. We transmit a signal from the transmitting antenna to the receiving antenna here. We transmit the signal through 5 megahertz. It will reach here after reflection. If you increase the frequency to 10, it will go to the ionospheric region and reflection takes place towards the earth. So again, if you increase the frequency to 15 megahertz, it will go directly to the ionospheric region. It will directly come after reflection to the receiving antenna. So here 15 is taken as MUF. That is the maximum usable frequency at which a wave is reflected from the ionospheric exactly towards the receiving antenna. We call it as the maximum usable frequency. Here in our example, 15 is taken as MUF. Now let us derive the expression for MUF, that is the maximum usable frequency for curved earth. So for curved earth, we know that the surface of the earth is not flat, the surface of the earth is not smooth at all places. Let us assume when the signal is traveling over the curvature of the earth. So what will be the maximum usable frequency for the curved earth? Now let us say, here there is a diagram here. This is the LN represents the curved earth. And O is the center of the earth. Here you can see here O is the center of the earth. And R represents the radius of the earth. And R represents the radius of the earth here. And here, basically, from the triangle LQO, there are some notations to be noted. If you take triangle LQO, if you apply sin theta here, for this triangle, sin theta is equal to LQ by LO. So that is opposite side to theta by hypotenuse. So what is the opposite side to theta here? Here LQ, the LQ is given by LO sin theta. LQ is equal to LO sin theta. So LO is nothing but R sin theta. LO is nothing but R sin theta. So LQ is written as R sin theta. So here we got this R sin theta just by applying the R sin theta value here. Similarly, you can find out by applying through cos theta also. So we can apply the cos theta also to find out any of the sides. Let us assume D. Let D is the distance traveled by the path from L to N. So from the transmitting antenna to the receiving antenna, let D be the distance traveled from the transmitting antenna to the receiving antenna. And let us assume theta I as the angle of incidence and theta R as the angle of reflection here. And R is the radius of curvature of the earth. And H here, H is the height from P to M. H is the height from the surface of the earth to the ionospheric layer, where we have denoted the point M here. H is equal to PM here. So these are the notations being used in our derivation. Now let us start our derivation here. So we know that from this, the total angle, arc by radius. So the total angle is given as here from this LON, the total angle is 2 theta. So 2 theta is equal to, angle is equal to arc by radius. So arc by radius here. So what is the arc here? The arc is, its value is d here as per the figure, and radius is taken as r. So 2 theta is equal to d by r, and the d is equal to 2 theta r. So we need to remember this value. So the distance traveling by the path ln is given, it depends upon the theta and the r value. So d is equal to 2 theta and r. So from this angle, we know that angle is equal to arc by radius. So the total angle at LON path can be described as theta plus theta here. We can write as 2 theta here. Theta plus theta is equal to 2 theta and 2 theta is equal to arc by radius. So this is we are going to find out the value of d, which depends upon the angle and the radius of the earth. So similarly, we can find out the value of LQ and QO path, and MQ can be found out. We can find out by this MQ here. From the figure, you can write as MQ is equal to OP plus PM minus OQ. So we want to find out the value of MQ here. So to find out the value of MQ here, we can write as OP. OP is nothing but this value, total value of OP, and plus PM, which is nothing but H. And here OP is nothing but, so the length of OP plus length of PM minus length of OQ gives the value of MQ here. So the length of OP is given as length of OP plus length of PM, it is taken as H, minus length of OQ. So this is the MQ value. So MQ from the figure we can write as the length of OP. OP is nothing but R, the total value is R, plus PM. PM is nothing but H, minus OQ. So OQ is nothing but, it is the value of R cos theta. We can write as R cos theta. So here, if you assume triangle LQO, for this triangle LQO, we can write cos theta is equal to adjacent side to theta, that is OQ, by hypotenuse, that is LO. So OQ is equal to LO cos theta. This is equal to R cos theta. So this we can substitute here. So OP plus PM minus OQ, and here OP is nothing but the radius from here to here, the radius R plus H minus R cos theta. So we need to find out the value of MQ for our derivation, and we can also find out the value of LM through Pythagoras theorem. Here we can also find out the value of LM by assuming the triangle LMQ. So from this triangle LMQ, if we apply the Pythagoras theorem, from the figure you can write, for this triangle LMQ, the Pythagoras theorem can be applied as LM square is equal to LQ square plus MQ square. So here LM is equal to root of LQ square plus MQ square. So here LQ square is nothing but the root of R sin theta whole square plus MQ square is equal to, just now we have seen MQ is equal to R plus H minus R cos theta. This is whole square. So we need to substitute this here in this value. So here we know that from the triangle, as M is the midpoint of L and N, LM is equal to MN. From the triangle you can observe that the value of LM will be equal to MN. So we need to find out all the necessary notations from the diagram, that is LM is equal to LQ square plus MQ square. So we have determined the value of MQ. We have determined the value of the R sin theta whole square plus H plus R minus R cos theta whole square. And we know that if we apply the cos theta I value from this figure, cos theta I is equal to adjacent side to theta here, cos theta I is equal to adjacent side to theta is equal to MQ by hypotenuse, that is LM. This is equal to cos theta I. But we know that F muff is equal to FC by cos theta I. So from this equation we will get cos theta I is equal to FC by f mof, fc by f mof. So equating these two equations, we'll get mq by lm is equal to fc by f mof. So this is if you assume this as equation 1, and if you assume this as equation 2, equating 1 and 2 equations, cos theta and cos theta, you will get mq by lm is equal to fc by f mof. So from this we need to find out the value of f mof for the curved earth. From this we need to find out the value of f mof for the curved earth. So cos theta I is equal to, we know that mq by lm here from the figure you can see here. From the figure cos theta is equal to mq by lm here. So mq we have determined already, h plus r minus r cos theta. And lm is equal to root of r sin theta whole square plus h plus r minus r cos theta. If you simplify this squaring on both sides, you will get cos square theta I is equal to h plus r minus r cos theta whole square. So here the square root will be cancelled here as we are squaring on both sides, r sin theta whole square plus h plus r minus r cos theta whole square. So we shall further simplify by applying simple math. Here we know that cos theta is equal to fc by f mof and cos square theta is equal to critical frequency by f square mof. So that equal to this equation. So from this equation you need to find out the value of f mof. We need to find out the value of f mof here. And we shall derive further to find out the value of glazing angle distance. That is what is the total amount of distance propagated by the transmitting antenna from the receiving antenna. So if we assume angle MLO as 90 degrees, as angle MLO as 90 degrees for this triangle, let us assume here MLO here. So for this triangle, let us apply again some theta formula here. We will find out the value of theta here. MLO is equal to 90 degrees here. Here this is the 90 here. Let us assume this as 90. That is, the signal is being transmitted at an angle of 90 degrees towards the ionospheric layer. Let us assume from L, the transmitting antenna, the incident ray is traveling at an angle of 90 degrees towards the point M, in the ionospheric region. So angle MLO is equal to 90 degrees. And under this consideration, let us try and take the triangle MOL. So cos theta is equal to, we can write LO adjacent side to theta by MO. So cos theta is equal to LO, we can write LO by M. So here what is LO here? R. So R by MO is nothing but M and O we can write as MD. MO can be written as MD plus MP plus PM. So cos theta is equal to LO here, the distance of LO is taken as R here. Here the distance of MP is taken as H plus R. So further simplification, you can write this as R by, if you take R as common here, 1 plus H by R here. So R get cancelled. So cos theta is equal to 1 plus H by R whole inverse you can write. So by applying the binomial series expansion, you can write this as, we know that 1 plus x whole power n is equal to 1 plus nx plus n square, x square and so on. So applying this binomial series expansion, we can write 1 minus h by r plus h square by r square and minus and so on. So here we know that the radius is, the value of radius is very high compared to the height of the transmitting antenna. So the higher order terms can be neglected. So overall, if you simplify here, we will get cos theta is equal to 1 minus h by r. So cos theta is equal to 1 minus h by r. The higher order terms can be neglected. H square, h cubed, r square and r cubed can be neglected. Why? Because the value of the radius of the earth is very large compared to the height of the transmitting antenna. The radius of the earth is measured in terms of kilometers, whereas the height of the transmitting antenna is measured in terms of meters here. So here cos theta is equal to 1 plus h by r minus 1. So from this binomial expansion we can get 1 minus h by r. So as theta is too small, we can write neglecting higher order terms, we can write 1 minus h by r here. So 1 minus theta square by 2 is equal to 1 minus h by r here, and theta square is equal to 2h by r here. So 1 minus theta square by 2 is equal to 1 minus h by r. Theta square is equal to 2h by r. Why? Because we know that 2 theta is equal to arc by radius. So arc is nothing but d by r here. So d is equal to 2 r theta here. So putting the value of theta in equation 4. So in equation 4, if you substitute, you will get d is equal to 2r into root of 2h by r. If you simplify this, you will get 4r square into 2h by r. If you further simplify and r get cancelled here, you will get root of 8h. So from this expression, if squaring on both sides, we shall find out the value of h as d square by 8r. So we are getting two values. One, the distance of propagation. The other one is h, the height of the ionospheric layer from the surface of the earth. So from the surface of the earth, the height is given by d square by 8r, which depends upon the distance of propagation from the transmitting antenna to the receiving antenna. So we can write cos theta is equal to 1 minus h by r, and 1 minus h values we have determined just now, d square by 8r. This is equal to 1 minus d square by 8r square here. So from triangle LOQ, we can write sin theta is equal to d by 2r. So from triangle LOQ, as per the figure, we can write sin theta is equal to d by 2r. So we have determined the values of sin theta and cos theta here. So we have substitute these equations in equation 10 here. So in equation 10, we need to find out, substitute this sin theta and cos theta, and if you simplify, you will get the value of maximum usable frequency. So here you can write cos square theta is equal to FCR by F square MOF. So this is the critical frequency, this is the maximum usable frequency. And if you substitute here the sin theta and cos theta value in the equation 10 here, and if you simplify, you will get here r get cancelled here. Multiply it h plus r minus r into 1 minus d square by 8r square, r get cancelled here. And the remaining terms after simplification is given by fc square by f square MOF is equal to h plus d square by 8r whole square by d square by 4 plus h plus d square by 8r whole square. So here from this equation you can find out the value of f MOF. You can find out the value of f MOF. So f MOF is cos theta is equal to fc by f MOF, and we know that f MOF is equal to you can write as fc into root of d square by 4 plus h plus d square by 8r whole square by h plus d square by 8r. So here from the figure we have determined the value of theta and theta I. We also determine the value of sin theta. We also determine the values of cos theta. So if we know that cos theta I is equal to fc by f MOF. So we determine cos theta I is equal to angle of incidence is equal to fc by f MOF. So after finding out the value of f MOF, we have found out sin theta, cos theta, and the distance which is related to the angle, and also the angle of incidence. So r the radius of the earth. Considering all these parameters, we need to find out the maximum usable frequency. So from this equation, you can say the maximum value frequency. The maximum usable frequency depends upon the critical frequency, the distance of propagation, the radius of the earth, and the height of the transmitting antenna, and the height of the layer, ionospheric layer from the surface of the earth. And moreover, from this equation also, we can derive the expression to find out the value of skip distance. The skip distance is nothing but the minimum distance at which a wave is returned to the earth for a fixed frequency. We call it as a skip distance. So if we indicate this d as, just indicate as d is equal to d skip here, and we shall simplify squaring on both sides. We shall simplify by squaring on both sides and find out the value of d skip. We will get the equation. So that equation is, this is the derivation to find out the expression for d skip for the curved earth. So from this expression only you can find out the value of d. You can find out the value of d. The next one is optimum working frequency. So the frequency normally used for ionospheric region is known as optimum working frequency. The simple definition for optimum working frequency is 85% of the MUF value, we call it as optimum frequency. So whatever the maximum usable frequency that we are using between the transmitting and receiving antennas, 85% of the MUF value, we call it as the optimum working frequency. The optimum working frequency between the transmitter and the receiver for ionospheric transmission is defined as the frequency laying between the 50% to 85% of the predicted MUF between the transmission and the reception points here. So it is observed that we know that the maximum usable frequency is not same during the daytime and the night times. So the muff value will vary from hour to hour or day to day basis, and also season to season or monthly basis. So as the optimum working frequency is selected as a fraction of maximum usable frequency, the optimum working frequency also varies in similar way as the maximum usable frequency varies. So here, so whatever the muff value we take either in the daytime or night time, similarly the optimum frequency value also varies during the daytime and the night times. So it is not possible to change the frequency during the from hour to hour or from day to night time. So hence the propagation of wave, two frequencies are used, namely while one frequency during the daytime while the other for the night time. So generally, whatever the transmitting frequency that we propagate during the daytime, the amount of signal strength during the night times will be reduced. Or during the daytime, the atmosphere is warmer here, and during the night time, the atmosphere is denser. So generally, whenever we transmit a signal, if 10 megahertz signal is sent from the transmitting arena, during the daytime, we get a 10 megahertz signal. But during the night time, there is a slight variation in this 10 megahertz signal. So this is daytime. But during the night time, this 10 megahertz signal will not reach to the receiving end. We get only 9 megahertz signal. We get only 9 megahertz signal. So there is some loss of energy taking place in the night time. So for the propagation of wave from the transmitting antenna, we are going to assume as two frequencies, one during the daytime, while for the night time. So this is the only solution for us to transmit the two different frequencies during daytime and the night time. And the other solution given for the transmission during the daytime to the night time is optimum frequency. So here, an optimum frequency is fixed whether it may be a daytime or whether it may be a night time. So irrespective of the day, irrespective of the night times, irrespective of the hours, we have fixed a frequency which is known as optimum frequency that is used as a transmission frequency from the transmitting antenna to the receiving antenna. So what is this optimum frequency? Means 85% of the muff value. So whatever the maximum frequency that we are initially decided to send from the transmitting antenna, 85% of the muff is treated as the optimum frequency. So sometimes it is preferred to have a third frequency even during the transmission from day night to night time. So it is observed in the mid time vertical height of the ionospheric layer increases as compared to that during the daytime. So thus the skip distance also increases. So the skip distance is also going to increase. If the skip distance is increased, the energy, the signal that is going to transfer towards receiving antenna will reach beyond the antenna. So it's going to reach beyond the antenna. So all the signal strength is not going to receive to the receiving antenna. The next one is lowest usable high frequency. The lowest usable high frequency is defined as the lowest frequency in the highest frequency band that is useful, satisfactory reception for the given transmission distance and power. Thus, for the useful ionospheric propagation, the frequency should be selected between muff and the lowest usable high frequency. So, lowest usable frequency or lowest usable high frequency defined as the lowest frequency in the high frequency band that is useful, satisfactory reception for the given transmission distance and power. So the LUF, that is the lowest usable high frequency, depends upon the effective radiated power, the ionospheric characteristic between the transmission distance, the radio noise of the receiver and the type of the receiver. So the lowest usable high frequency depends upon the effective radiated power, the ionospheric characteristics between the transmission distance and the radio noise of the receiver and the type of the receiver. Now let us come to the another topic which is known as the actual height and the virtual height. So the actual height and the virtual height are two important parameters of skywave propagation. The actual height is different from the virtual height. So for long distance communication, the skywave propagation is effective due to the presence of a different ionosphere layer which act as a radio mirror. So ionospheric layer, it is one important layer which is used for long distance communication so that we can transmit the signal for 500 kilometers or 1000 kilometers through the process of reflection and refraction phenomena. So when the skywave used for long distance communication reaches a given ionospheric layer, the ionization density increases and this in turn reduces the refractiveness of the layer. So according to the law of refraction, as the wave enters from the rarer medium to the denser medium, it bends gradually further away from the normal and follow the path LMN as shown in the figure here. So you can see here in the figure, whenever we transmit the signal into the ionospheric region, whenever it is going to travel from the denser medium to the layer medium, when the wave bends away from the normal, at a certain point, it almost becomes parallel to the layer. So it almost becomes parallel to the layer and bends further toward. Such a wave finally emerges out of the ionospheric layer at an angle equal to that of incidence. So here the angle of incidence is equal to the angle of reflection, where the wave is going to bend and reflection happens from the ionospheric layer, that we call it as the actual height. So where exactly the reflection phenomena exists without refraction, this we call it as the actual height here. And the virtual height is given by this path here from O to, suppose this, let us assume this is A. So OA path, it is known as the virtual. This is known as the virtual, and AM path, we call it as the actual height here. Actual height here. The height at a point above the surface at which the wave bends towards the earth is called actual height or a true height. However, below the ionized layer, the incident and the reflected waves follow the paths which are exactly the same if reflection takes place along path above the earth's surface, which is greater than actual height of the layer. Such height is called as virtual height, which is denoted by h. So here the wave is traveling. What is the time taken by the path? You can say here speed is equal to, we know that speed is equal to distance by time here. Time is equal to distance by velocity here. So here the distance is nothing but 2h. Why? Because this is the h value. The wave is traveling in two different paths. This is one path and this is another path. So this is 1 and this is 2. Hence the distance traveled is nothing but 2h here. The distance traveled by the electromagnetic ray from point A to point B is 2h. So we can write this value as t is equal to 2h by c. So from this equation we can write as h is equal to ct by 2. So h is equal to ct by 2. H indicates the height of the virtual height. We can indicate as hv. That is, the virtual height is given, depends upon the velocity and the time taken by the ray to travel from point A to point B. So hv is equal to, we can write as ct by 2. hv is equal to ct by 2, the virtual height. Let us find out the skip distance here. So the skip distance, it is nothing but the shortest distance from the transmitting antenna which a sky wave of fixed frequency will return back to the earth. So whenever we are going to transmit a signal with some angle here, we are going to transmit with a fixed frequency. The frequency is fixed here, and we are transmitting here with some angle. The angle of incidence is different at here. From this angle, the wave is going to reflect back here. And if we, let us assume this is one path, and if we take another angle, if we transmit the signal from with another angle, it is going to reach to the receiving here. This is A and this is B. So here the wave is returning to the point A with the minimum distance. So this distance we call it as a skip distance here. So here the wave is going to return the shortest distance at which a wave is returned to the earth for a fixed frequency. We call it as the skip distance. So this skip distance or the minimum distance or the shortest distance, it depends upon the angle. We call it as a critical angle. So always we need to remember that the angle of incidence that we are going to send, it depends upon the critical angle. That means the angle of incidence must be greater than the critical angle so that the minimum distance is achieved. With this rule, that is theta I must be greater than theta c. So higher the frequency, lower is the critical incidence. So let us see what is the critical angle here. So the angle of incidence at which a wave is returned to the earth at minimum distance. The angle of distance at which a wave is returned to the earth at minimum distance, we call it as critical angle. Or the angle of incidence in denser medium for which the angle of refraction is 90 degrees, we call it as the critical angle. So let us say with an example here. Here there is a boundary here. This is the boundary between the denser medium to the rarer medium. Let us assume here there is a normal is there. So here this is known as the angle of incidence here. Let us assume this angle of incidence. Assume the signal is being transmitted at an angle of 10 degrees. At an angle of 10 degrees. So we know that when the wave travels from denser medium to the rarer medium, the electromagnetic ray refraction takes place and it moves away from the normal. The ray moves away from the normal. So this is the normal here. It moves away from the normal. It will be like this. If we take another angle here, this is the, let us assume here there is a 20 degrees here. The angle of incidence is 20 degrees. And this is the normal here. If we increase the angle of incidence, again refraction takes place. The refracted ray will be normal here. It will be like this. This is the refracted ray which is away from the normal. So which is away from the normal. So this is the refracted angle R here. And if you further increase the angle, from 20 to 25, the refracted ray will be striking the surface of the boundary. That means the refracted ray here, it is parallel to the boundary. It is parallel to the boundary. So here the angle of incidence where the refracted angle is 90. Here this is the angle is 90. The angle of incidence where the refracted ray is 90. We call it as the critical angle. Now 25 degrees is the critical angle. We call it as theta c. So here the angle of incidence at which the refracted ray it is 90 degrees. We call it as the critical angle. So whenever we are going to transmit so for us reflection will happen only when theta is greater than theta c. That means the reflection will occur here if we transmit a signal greater than 25 degrees. So we are transmitting from 26 degrees here. If we transmit the signal with an angle of 26 degrees, the ray will be reflected towards the receiving antenna like this. So the angle of incidence will be equal to the angle of reflection here. So this is the critical angle. We know that 25 is the critical angle. So for reflection to occur, so we need to transmit a signal with more amount of critical angle. With an incident angle, there is more than the critical angle. So 26 is greater than 25. Hence reflection takes place. So to achieve minimum distance, we need to transmit a signal that is greater than the theta c. So minimum distance can be achieved at theta I is equal to theta c. So it depends upon the this minimum distance or the critical angle. It depends upon the frequency of operation. The skip distance depends upon the frequency of operation. It depends upon the height of the layer. It depends upon the height from the surface of the earth to the layer. It depends upon the thickness of the layer. So the skip distance depends upon the frequency of operation, the height from the surface of the earth, and also the thickness of the layer. So this is about the critical angle. So you can see in the figure here. So when we propagate, skip distance is nothing but it is the shortest distance at which a wave is returned to the earth from the ionosphere for a given frequency. So here the frequency is fixed here. So when we change when we send the angle of transmitted ray with some minimum angle theta 1, so the path is L path here. And if we transmit change this angle of inclination, that is theta 2, you can see the M path here. And if we transmit with a critical angle, at critical angle theta is equal to theta c, then it is going to reach the path B. So at critical angle theta I is equal to theta c. So this is the shortest distance. So either if we transmit the signal theta I greater than theta c, the d is more, the distance of propagation is more if we increase the value. So at theta I is equal to theta c, the distance will be minimum. So this is known as the skip distance. So just now we have derived an expression of MUF, that is the maximum visible frequency. From this equation we can find out the value of d skip here. So this is the derivation. F MUF is equal to Fc into root of d skip by 2h whole square. So from this we need to take out this value d skip outside from the square root. And if you simplify, you will get d skip is equal to 2h into root of F MUF by Fc whole square minus 1. So let us see what is the multi-hop propagation. So what is the multi-hop propagation. So let us consider the path followed by a wave from the transmitter T to the receiver R as shown in the figure. So you can see here from T to R, we are going to transmit a signal. The signal is being traveled in two different paths. One is A and one is B here. So A is one path and B is the other path here. Here low is known as the lower ray. We can also say as a lower ray. B is known as the upper ray. So when we compare the densities of the field strength of A and B, A is having the higher density value. A is having the higher strength. The field strength of A is very high compared to the B. So here though A strength of the A is very large, we can transmit the signal through the path A for shorter distance only. For short distance only. So here you can see here, the path A is the lower ray while path B is the upper ray. So we have transmitted a signal here. This is the A and this is B here. If we transmit a signal through a single path, we call it as a single hop propagation. Here hop means hop represents as path here. Here hop represents as path. So here if a wave is traveling in single path from transmitting antenna to receiving antenna, we call it as a single hop propagation. If the wave is traveling in two different paths, we call it as a multi-hop propagation. Multi-hop propagation in two different paths here. So here we can have the transmitting antenna here, which is for example here, there is a receiving antenna, transmitting and receiving, and this is one ray and this is another ray. So we want to establish a communication between the transmitting and receiving antenna. So the upper ray is known as a Peterson ray. The lower ray is strong in terms of energy. So we know that this is the A and this is the B. The lower ray is the A. It has this large amount of energy compared to the B. So upper ray is with the larger angle, it spreads more as compared to it becomes weaker. So B is having the larger path, it is going to travel a larger distance, hence the energy of the path B will be very less compared to the path A here. So, but many times it is observed that the lower ray cannot reach the receiver from transmitter in single hop due to the following reasons. So, you can see here, though the transmitting antenna and receiving antenna, the lower ray is stronger, it cannot reach to the receiving antenna due to the curvature of the earth and due to the distance between the transmitter and receiver is greater as compared with the skip distance. Hence, under such conditions, a multi-hop communication link is used for communicating a wave from transmitter to the receiver. So in practice, the minimum angle at which a radio wave leaves the transmitter is usually 3.5 degrees above the horizon. So whenever we want to transmit the signal from the transmitting antenna, the transmitter is usually above 3.5 degrees above the horizon. So we know that the E layer and F2 layer, the maximum skip distances are about 1700 to 3500 kilometers approximately. So when the distance between the transmitter and receiver is greater than the skip distances of E and F layers, the wave takes 2 or more hops before reaching the receiver as shown in the figure. So generally, whenever we want to propagate a signal around 1700 kilometers or 1500 kilometers, so for E and E layer, the skip distances are 1700 to 3500 kilometers, E layer and F2 layer. So such a high distance to travel, we need to establish a communication which is through multi-hop communication. Here. So we are going to transmit here the signal here from a transmitting antenna here. Here the refraction takes place here. One refraction is going to take place. And here when it touches from E layer to F layer, this is from the denser medium to the rarer medium. Refraction takes place here. So it is going to travel and touch the curvature of the earth here. Here the reflection is happening here. Reflection happens and it's going to travel again. It is going to touch the F layer again here. Here the refraction is happening here again. So like this, the same path is traveling in multi-hops, multi-paths. See, this is one path, second path, third path, and fourth path. So, through multi-hop propagation, we can transmit a signal for long-distance communication for even 500 kilometers or 1000 kilometers. This gives one of the types of multi-hop propagation. So, by reflection from E to F layer, also we can also transmit. The signal if the layer is propagating sandwiched between two layers. So here we are going to transmit a signal from transmitting and receiving antenna. Here the signal is being sandwiched within the layer. That means the signal is a reflection and refraction phenomena are between the F layer and the E layer. The signal is not being reached to the receiving antenna. The signal is not being reached to the surface of the earth. It is going to here the reflection is happening here. Again here the reflection is happening here. Reflection is happening here. The refraction is happening here. Again here the refraction is happening. So like this. So many number of paths within the layer. After traveling many number of paths, finally the wave is going to reach to the point, or that is the Earth's surface here. So here you can see here multi-hub propagation. The E layer and F2 layer, the maximum skip distances are 17,500 kilometers approximately. So when the distance between the transmitter and the receiver is greater than the skip distance of E and F layers, the wave takes 2 or more hops before reaching receiver. So whenever the distance between the transmitter and the receiver is greater than the skip distance, that is, we want to travel around 1000 kilometers or 700 kilometers, the radio path, then it takes more number of hops before it reaches to the receiver. So this is a communication, we call it as multi-hop communication or multi-path propagation or multi-hop propagation of the wave. So the lengths of hops involved in the propagation are unequal. So in most cases, the actual frequency used in the communication link is less than the maximum usable frequency. So in most of the cases, the actual frequency used in the communication link is less than the maximum usable frequency. So then the waves are transmitted to the receiving point located at a distant point by 2 or more hops. So the transmission of electromagnetic waves between transmitter and receiver may take place as below. So by direct reflection from a single layer, this is called single hop propagation. So you can see here when we are going to transmit a signal from the transmitting antenna to the receiving antenna, in single path we can also transmit. In single path we can also transmit. So there is a single path existing when it touches any one layer. It may be the D layer or E layer. So when it touches the E layer, the signal is going to refract directly to the Earth's surface. It is going to bend slightly here, and path is carried on the curvature of the Earth towards the radius, towards the point R here. You can also see here the multi-hop propagation by refraction of E layer, incidence on F layer, the reflection from the F layer finally reflected back to the Earth by refraction of the E layer. So you can see here in the as shown in the figure, the refraction is going to happen here. One refraction is going to happen here, and again here the reflection is happening here. Back to the Earth by refraction of the E layer here. So like this, many number of refractions and reflections, the wave is going to travel in multi-paths. Hence the name is given as multi-hop propagation. Here the multi-hop propagation is carried between E and F layers. So the multi-hop propagation is carried between the E and F layers. So today we have discussed about the skip distance. Let us have a recap of what we have studied today. The skip distance is nothing but the shortest distance at which a wave is returned to the Earth for a given frequency. We call it as a skip distance. And we have seen the derivation of the MUF for covered Earth. We had seen the MUF value, that is the maximum visible frequency for covered Earth. So F MUF is equal to Fc into root of 2h by F MUF whole square minus 1 here. And also we have seen the virtual height. The virtual height is given by HV is equal to Ct by 2 here. The virtual height and the actual height both are different here. So where the reflection takes place is the actual height. Where the wave is going to touch the topmost layer, we call it as the virtual height here. And a single hop propagation means if the wave is traveling from the transmitting antenna in single path, we call it a single hop propagation. And multi-hop propagation means the wave is going to travel from the transmitting antenna in different paths, in many paths before it is going to reach to the receiving antenna. So all these concepts you can refer the textbook, either K.D. Prasad, the Antennas Wave Propagation by K.D. Prasad, or you can also refer U.A. Bakshi. You can also go for Balanis, that is the Antennas Waves and Propagation. Or you can also refer Cross also. John D. Cross for these concepts of multi-hub propagation, single-hub propagation, skip distance, and the derivation of muff for flat earth and the curved earth. So let us close the session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.